All right, 11-4. So we've done all of the counting techniques, fundamental counting principle, permutations, combinations. 11-4, or 4, yeah, 11.4. We're going to talk about probability because the reason why we've been dealing with all those fundamental counting principles and permutations and combinations was to get the total number of outcomes, and probability is all about knowing those total number of outcomes. So 11.4, we're going to talk about some basic information as far as probability goes. Ooh, I'm showing you the wrong slide. I need to go back to the beginning, but that's all right. So let's go back to the beginning. So there are two kinds of probability that we're going to talk about. There is what we call theoretical, and then the other one is what I call experimental, or the book calls it empirical. But experimental, empirical, they both mean the same thing, okay? So 11.4 is going to talk about those two different pieces. Most of us who are very familiar with the theoretical, and that's what we base all of our life information about, okay? But in general, let me just backstep for a moment. The reason why we went all through those counting techniques is so that we can start now in 11.4 all the way through the end of this, start talking about probabilities. Okay, and again, probabilities all base that in the end, when we make our fractions, it's all about some of those total outcomes that we were able to generate from 11.1, 11.2, and 11.3. So theoretical probability, this is what it looks like. So a little bit of new notation. You have a P, and then you have a parenthesis with the event, whatever the event might be. You'll understand that here coming up. But how we do theoretical, it is the number of event outcomes. So what we want to happen, how many different ways can that happen? See, there's kind of a counting technique right there. How many ways can the event happen over the total number of outcomes, okay? So right there at the bottom, that's why we learned 11.1, 11.2, and 11.3, because there at the bottom, that's where sometimes we might have to use that fundamental counting principle. We might have to use permutations, combinations, but more of that's going to come involved in 11.5 here in a moment. Right now in 11.4, we're going to focus in on basic probability. So don't worry about fundamental counting principle, permutations, combinations in here. We're going to kind of step back from that a little bit. But we're going to do some basic probability. So again, theoretical probability, most of us deal with that. Like when we flip a coin, okay? If I want to know what the probability of flipping heads is, many of you are going to be like, Mr. Armstrong, it's 1/2. And I'll be like, yes, that's correct. Because there is only one way to flip a heads, okay? But on the bottom, the reason why there's two is because there are two outcomes. You either flip heads or you flip tails, okay? And that probability of 1/2 is what we call theoretical, okay? Because that is, in theory, what should happen. There's only one way to flip heads, and there are two outcomes, so that's 1/2. That's the idea behind theoretical. And again, we've dealt with that before. And the same thing like when you roll dice. Like in Yahtzee, this is where that probability kind of helps you, in being able to figure out, what is kind of the better move. In dice, when you roll dice, there's only 6 outcomes to roll in a die. 1, 2, 3, 4, 5, 6. So if we talk about the probability of rolling a 3, well, how many ways can you roll a 3? 1. There's only one side of a die that has 3 dots. Out of how many outcomes? Well, how many sides are there? How many different ways can we end up with an answer? There are 6. So the probability of rolling a 3 is 1 out of 6. Okay? In here, all of your answers are going to be fractions reduced. So, which is why in our calculator, we're going to use our best friend, alpha y equals, to let it do the dirty work. Okay, and then again, remember, you just put your numbers in, 8 over, let's say, 40, and there it is. Let the calculator do the dirty work, okay? So, going back to this, let's do some theoretical probability. I have lots of different examples here, everything from flipping coins, tossing dice, to real world examples, spinning a spinner, drawing cards. This is going to be the section where we start talking about cards now, and you need to be able to draw cards, okay, from a deck. So we're going to talk about a standard 52 card deck. If you don't actually have a standard deck of cards at home, go to the dollar store. Buy a cheap $1 deck. That way you can explore, deck of cards right there in your hand. Have it, actually textually there. But I will show you all the information about a deck of cards and tell you in your book, your digital book, where you can locate one. Okay, so lots of stuff for theoretical that I have already here. I wish we were in class because I bring in my bag of probability, and we actually do a lot of this right then and there. Okay, so right here it says a die is roll. The set of equally likely outcomes is 1, 2, 3, 4, 5, 6. So we just kind of talked about something like this. So I've got 4 probabilities here. Go ahead, give them a shot. See what you think. Again, probability, theoretical, is what you want to happen for the total number of outcomes. And inside that parenthesis, that's what I want to happen. So right up here, this P parenthesis 4 means that what is the probability of rolling a 4? Down here, this P odd means what's the probability of rolling an odd number? Right over here, this means what's the probability of having a number less than 20? Okay, right here, what's the probability of having a number greater than 8? My stuff keeps flying around. Yay. So that's all it means. So give them a shot. Hopefully you pause the video too. All right, so let's talk. So probability of rolling a 4. Well, this is just like the probability of rolling that 3 I talked about a second ago. How many ways can we roll a 4? 1 out of. How many ways are there total? We'll look right up here. 1, 2, 3, 4, 5, 6. There are 6 total outcomes. So it's 1/6. And that does not reduce. Okay? And if you have trouble reducing, go into your calculator and put in 1/6, hit enter, and see if it reduces or not. Okay? Because they want the fraction answer. Let's jump down here to the probability of odd, and then we'll jump over there to the other 2. Okay, what is the probability of being odd? Well, how many answers are odd? Well, if you look up here, 1 is odd, 3 is odd, 5 is odd. So how many times can that outcome happen? There are 3 times that outcome can happen. So our top number is 3. Out of how many different outcomes? There are 6 again. The bottom number on these should be 6 because that's the total number of outcomes. Now, 3/6 does reduce to 1/2. That's what the My Math Lab would want, the 1/2. Okay? There we go. So over here, what's the probability of rolling a number that is less than 20? So what answers are less than 20 up there? Well, if you said all of them, you are correct. So we have a probability. I mean, how many ways can this event happen? Well, we just said all those answers up there are possible. So that's 6. I have 6 ways of rolling a number that is less than 20. Out of how many choices? Again, I just said this a moment ago. There's only 6 outcomes. In the end, what they really want in My Math Lab is the number 1, because you have 100% probability of that coming true. Okay? Your probability of rolling a number less than 20 is 100%. All right, down here, rolling a number greater than 8. Well, if you look up there, how many numbers are greater than 8? None. So how many ways can that happen? None. Out of how many ways? 6. But do not leave it as 0/6. They want it to actually be 0. So what's the probability of rolling a number greater than 8? It is 0. So just so you know in here, you will end up with fractions. okay, most of the time, but it is possible to have an answer of 1, meaning that it is 100% going to happen. Or you could have a number end up being 0, which means that there is no way it will ever happen no matter what. Okay? So like that probability of rolling a number greater than 8, it ain't going to happen whatsoever. All right, let's take a look at another situation. So here it says, select a family with 3 children. The set of equally likely outcomes for the children's genders is MMM, MMF, MFM, MFF, FMM, FMF, FFM, FFF. Okay? Now, the order of these matters, so if many of you are thinking, Mr. Armstrong, isn't MMF and MFM and FMM all the same? No, they are not, because we are talking about children being born, and that means that some of these are older than the other one. And so, think of this when you're looking at these children's gender as the first letter represents the firstborn, then the secondborn, then the thirdborn. Okay, so those 3 are different answers because their ages will be different. They are different people. Okay, not the same. All right, so down below here, now that you know what you got, we've got that set up there. And I've got 3 probabilities that I want you to figure out for me. What's the probability exact of picking one family that has exactly 1 female? Okay, so that's what that means. The probability that we're going to grab a family and they have exactly 1 female. And then find me the probability that if I pick a family that there is at least 1 male. And then find me the probability that if I pick a family, at least 2 females are in my choice. So give it a shot and go. Pause the video. All right, so let's take a look at these and let's start talking about this. So if you look up here and count this up, you already know what your bottom number will always be. 1, 2, 3, 4, 5, 6, 7, 8. So all of these fractions in here are going to have a bottom number of 8. Question is, what's the top number, and then if it reduces. Okay? So for this first one, it says exactly 1 female. No more, no less. Well, how many times does that happen? That one right there has exactly 1 female. This one next to it, the MFM, has exactly 1 female. The FMM has exactly 1 female. Everybody else up there either has no females, 2 females, or 3 females, and we don't want those. We want it where there is exactly 1. So our top number up here is 3. And then, of course, you always need the question, does 3 over 8 reduce? And it does not. So that would be the final answer you put into my math lab. Okay? So our next one. So it says at least 1 male. And we've talked about this word at least before. Okay? So that means you can have 1 male. At least also means you could have 2 males. Because it is at least, you could also have 3. So you need to look at all those possible cases. Where is it that I have 1 male, 2 males, 3 males? Because that's what at least means. The lowest number of males you can have is 1 or more than that. That's at least. Okay? Or another way to think about it, greater than or equal to 1. Okay? That's what at least means. It's greater than or equal to. So I definitely have at least 1 male with MMM. I definitely have at least 1 male with MMF. I definitely have at least 1 male with MFM. I definitely have at least 1 male with MFF. I definitely have at least one male with FMM. I definitely have at least one male with FMF. And finally, I definitely have at least one male with FFM. So how many outcomes is that? 7. And does 7 over 8 reduce? No. So that stays the way it is. All right. So one more here. At least 2 females. At least 2 females. So again, we just talked about the at least one male. 2 females should be pretty easy. So if we come up here and take a look at least 2 females. So that starts right here. I have 2 females, so that's good. I have 2 females. Yep. 2 females. Yep. And then the 3 females is included in this one because of the at least. So how many outcomes do I have there? 4 out of 8. And does that reduce? Yes. To a half, and that's what we would want. See, nothing crazy. They're providing you with all the information you need. You just got to use it. Okay? And think about what's going on. All right. So right here it says a single die is rolled twice. The 36 equally likely outcomes are right there. And again, this picture is in your book. All this stuff I'm just stealing straight from the book. These would be examples that we would have done in class together. So right here you can see all the examples. The first number right there is what was rolled the first time. The second number is what was rolled on the second time. Okay? So all of these are different answers. Okay? Because the first number represents the first roll and the second number represents the second roll. So 2-1 is not the same answer as 1-2, okay, even though they consist of the same numbers. They are different. So there are 36 outcomes there. Now you know what the bottom number for all of your fractions are going to be. Keep that in mind. So down below here, using that little chart right there, find me the probability of rolling 2 evens. Find me the probability that the sum of the die, the 2 rolls added together, is equal to 5. Find me the probability that the sum is greater than 12. And go. Pause the video. Okay. So you already know what the bottom number to all these fractions is going to be. This guy is going to be over 36, 36, 36. Okay? All we got to do is start finding the top numbers. So 2 evens. Well, if you look up here, anybody that is odd for the first roll, like 1, 3, 5, you can throw that entire row out. Anybody that is odd for the second, we can also throw those columns out. Now all that's left are all the ones that are evens. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is 9 over 36, and that reduces to, if memory serves me correct, 1/4. And there you go. That's your probability of rolling 2 evens. What's the probability that I have a sum of my 2 die equal to 5? Well, let's go up here. Let's do some quick erasing. So if I want a sum of 5, well, There's a sum of 5 because 1 plus 4 is 5. 2 plus 3 is 5. 3 plus 2 is 5. 4 plus 1 is 5. And that should be it because everything else is either less than 5 or over 5. Okay? So how many times or how many ways is that going to happen? 4 Z's. And 4 divided by 36 as a fraction yields 1/9. There's the probability of rolling 2 die and having a sum of 5. And then last but not least, the probability of having a sum that is greater than 12. Well, if you look at the last case right here, that's the largest roll possible. So it is 12. So is there any way of rolling 2 die and getting a number bigger than 12? Absolutely not. So the answer is 0. Like I said, watch out for those zeros. There you go. See, nice, simple, and straightforward. I told you all this probability is going to be straightforward. They're not trying to throw tricks at you. All right, the spinner problem. So assume that it is equally probable that the pointer will land on any one of the 10 colored regions. And if the pointer lands on a borderline, spin it again. Okay, so there's what the spinner looks like. Okay, there are 10 regions. 3 browns, 3 reds, 2 blues, 2 yellows. Okay, so now if I give you the full page, here are the probabilities I want. What's the probability of being red? And then what is the probability of being blue? Okay, so you already know what the bottom numbers to these are going to be. So give it a shot. Pause your video. All right, so let's do this. So what is the probability of being red? Oh, and as we talked about earlier, we already know that the bottom numbers to these are going to be 10. And let me go back to my normal page width. We already know that the bottom numbers are going to be 10. Okay? Well, if we look up here, what's the probability of being red? Well, how many reds are there? Well, there's 1, 2, 3. So the top number is 3. Does 3 over 10 reduce? No. And there it is. That's the final answer. Down here, now it says red or blue. So we can either spin a red or spin a blue. Well, how many of those outcomes are there? Let's talk about that. Well, we already know that there are 3 red, right? Well, how many blues are there? Well, there are 2 blues. So how many outcomes are possible to be a red or a blue? There are 5. So that's 5 out of 10, which does reduce to a half. Okay? There you go. All right, last but not least, for theoretical, we're going to talk about a 52-card deck. 52-card standard deck includes no jokers. Okay, there are no jokers. Usually, you have that 54-card pickup game that we so love to play sometimes with our friends and everything like that. And usually in a 54-card deck, there are 2 jokers, a red joker and a black joker. Or sometimes they change the color up of the joker, and sometimes it might be green or whatever. They do weird things with jokers. In a standard 52-card deck, there are no jokers, so you know that. So let's start breaking down a 52-card deck, because it was very interesting to me that when I moved down here from Missouri, not a lot of people know about a deck of cards and how it all breaks down and things like that. So I want to make sure that this slide right here available to you, and I'll tell you where in your book you can actually look at the picture of the 52-card deck. But again, I highly encourage you to go out and get a deck that you can actually have in your hand and things like that, and kind of work these things out tangibly right there with you. Okay, so in a standard 52-card deck, there are how many colors? There are 2. You either have black cards or red cards. And since the deck is split into two colors, that means in total, for taking 52 cards and cutting it in half, there are 26 black cards and 26 red cards. 26 black and 26 red. Now, within these black and red cards, we break them down even further into how many suits. Okay? Suits are representative of a different type of card that they could be. So those of you that know cards, you already know the answer to this. Those of you that don't, in black cards and in red cards, there are 4 suits. And there they are. They are the club, the spade, the diamond, and the heart. And that's moving from left to right up there. So this is the club, the spades, the diamond, and the heart. Club, spade, diamond, heart. Okay, you will see me draw clubs and spades and diamonds and hearts. Just so you know, I make fun of my own drawings because when I draw my spade, it kind of looks like my spade. It looks like a butt that's having a fart come out of it. See, look, it's a butt with a fart. When I draw my clubs, they look like atom bombs. Whee! Looks like an atom bomb blew up. So, have fun making fun of me all you want because I make fun of myself. So, clubs and spades, that's what they look like. And since the black cards are being broken down into 2 suits, that means the clubs and the spades, there are 13 cards for those, and the same thing for the red. Since the red cards are being broken down into 2 suits, each one of those suits has 13 cards. Okay, so the 52 card deck breaks down into 2 colors, black and red, and those colors break apart into 2 suits, clubs and spades for the black cards, which have 13 cards each, and diamonds and hearts for the red cards, which have 13 cards each. Okay, and then those will now break down. So now we're going to talk about what happens in every suit. So every suit has the following information. Every suit has what we call number cards and picture cards. Okay? Or picture cards is what the book calls them. I call them face cards because sometimes it's just a face. So there are number cards and picture cards. Again, I call them face cards. So if you hear me say face cards, I mean picture cards. Number cards are exactly what they sound like. They have cards with numbers on them. Okay. Picture cards are ones that actually have drawings on them. So in the number cards, you have 10 actual number cards. In the picture cards, you actually have 3 picture cards. And here's what they called them. Okay. So just kind of giving you some information here about the numbers and the pictures for every suits. So in the number cards, the ace is considered the 1. I don't know why I put an extra 1 up there in there. That shouldn't be there. Let's fix that. So, undo. Okay. Ungroup. I don't know why I put the 1 in here. That shouldn't be there. Because the ace represents the 1. I want to make sure I fix that. So put this all back together then. Select all. Group. There we go. All right. So number cards is ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, again, the ace is representative of 1. In picture cards, you have the king, the queen, and the jack. Okay, those are your 3 picture cards. In total, there are 40 number cards, 10 for each suit. So there are 10 number cards in the spade. There are 10 number cards in the club. There are 10 number cards in the diamonds, and there are 10 number cards in the heart. And the same thing for the jack, the queen, and the king. There are 3 in the spades, 3 in the clubs, 3 in the hearts, 3 in the diamonds. For 12 picture cards total and 40 number cards total. Just some breakdown of some numbers there for you. Okay, and again, just reiterating what I said, there are 4 of each type of card because every suit has the same number cards and picture cards. So there are 4 aces: ace of spades, ace of clubs, ace of diamonds, ace of hearts. There are 4 tens. There are 4 king cards. Okay? So every suit has one of those, which means that there are 4 of each type of card. Again, as I said, 1 for each suit. And down below here, this is what they all look like. Again, I just grabbed this book or this picture from your book. Okay? There is a standard deck of 52 cards right there in front of you. You can see all the number cards. And then these are all the picture cards. Okay? There you go. All right, so now it's time to use this information and do some probabilities. This will be our last theoretical probability. Then we will talk about experimental. So here I have, I believe, a total of, okay, there are 6 probabilities here. So let me expand this page. Go ahead, pause the video, find me the probabilities. Okay, so what is the probability of a queen? Now, again, since we are a 52 card deck, you already know the bottom number for all these. It's all going to be 52. Okay, so every single fraction up here will be 52. Go back where you were. The question is, once you're done, is does it reduce? Okay, and again, we have our calculator to help us out with that reducing. So queens, what's the probability of a queens? Well, how many queens are there? Again, remember there's 4 suits and every suit has picture cards. So that means every suit has a queen. So there are a total of 4 queens. Queen of diamonds, queen of hearts, queen of spades, queen of clubs. So 4 over 52 does reduce to 1 over 13. And that will be the probability that they're looking for. Picture cards. Okay, what's the probability that you're given a picture card or you draw a picture card? Okay. The picture card, well, how many picture cards are there? I even actually told you that on the previous slide. So there are 3 picture cards in every suit. There are 4 suits. So again, from that previous slide, I told you that there are a total of 12 picture cards. So if you take 12 over 52, put that in the calculator, hit enter and let it reduce. That's 3 over 13. Okay. Again, I've shown you how to put these in the calculator before, but just to show you these two, since I haven't been jumping over to the calculator, you hit your alpha y equals. You want number 1. You put the 4 in from the queens. There were 52 cards. Hit enter. See, there's the 1/13th. Alpha y equals. Grab your fraction. You put the 12, which was the number of picture cards, over 52 cards. And there was the 3 over 13 that we got for the picture card reducing. Okay? So let the calculator do the work for you. Diamonds. How many diamonds are there? Again, if you look at my previous slide, I told you how many diamond cards there were. There were a total of 13. You got it. So if you put 13 over 52, 52, reduce it, you get 1/4. And that makes sense because there are 4 suits, okay? And you want only diamonds, so that's 1 group out of the 4. All right, so this next one make you think a little bit. So I want you to have a card that is bigger than 3 and less than 7. So what cards does that include? Well, if you're bigger than 3 and less than 7, that's 4, 5, and 6. So those are the only cards we care about. Well, how many of them are there? Well, remember, there are 4 of these, one for every suit. Okay? So that means there are 4 fours, there are 4 5s, there are 4 6s. 4 fours, 4 5s, and 4 6s. So that's a total of 12 cards. Because 4 plus 4 plus 4 is 12. So we already know what that reduces down to. 12 over 52 is, whoops, sliding down a little bit. That's all right. 12 over 52 is 3 over 13. And there you go. And then the final 2-1. Very, very specifics on these. So how many cards are there of an ace of clubs? How many aces of clubs are there? And if you go back and look at that picture, there's only 1 ace of clubs. So that's a very specific card that you're wanting to try and pull out. You want to be an ace and you only want to be a club. So there's only 1 ace of clubs. Does that reduce? Nope. It's good the way it is. Okay? And then last but not least, the card that you pull out must be a diamond and a spade. Is it possible to pull out a diamond and spade card? That means you're a diamond and a spade at the same time. Can you be a diamond and a spade at the same time? No. So what's the probability of pulling a diamond and a spade? 0 out of 52, which is 0. There's that 0 sneaking back in. See, not too bad. I know it can be very confusing at times. So, if you don't have an actual deck, go get one. Go to the dollar store, buy it for $1, or, go back and look at that picture that I gave you right here in your notes. Okay. I just took that picture straight from our textbook in section 11.4. It's in the actual reading part of the section. Okay. And that right there, that is theoretical probability. The number of your wanted outcome, your event, over the total number of outcomes. Okay? Last but not least, we're going to talk about experimental. Your book calls this empirical. It's just experimental. And it's exactly as you sound. You're going to do an experiment. So say we're going to take and we're going to flip a coin. And we're going to figure out what is the probability of flipping heads in that experiment, or what was the probability of flipping tails in that experiment, or maybe we'll do an experiment of rolling die where I'm just going to roll the die and I'm going to record my answers and I can figure out from my experiment what was my probability of rolling a 1. Okay, experimental probability sometimes comes up different than the theoretical. That's why there's different types. Okay, really experimental probability really shines the best when you're doing a lot of like statistical data with like surveys and things like that. That's where experimental data or experimental probability really shines. It's when you're talking about, the data and the percentage of people in your survey that did one thing versus another. If you take probability with me, which I am doing in the summer, we dive into that. Okay. So, and that would be the summer of 2020. All right. So, experimental probability is a lot like theoretical. Okay. Again, it's the same notation, P with your event, but this time on top is the number of times the event actually occurred. Okay. So, whatever your event is, the top number is the number of times it actually happened. Okay. The bottom number is the total number of trials. How many times did we do the experiment? How many times did we flip the coin? How many times did we roll the coin? Or excuse me, not roll the coin, but roll the die. Okay. That's all it is. It's just like theoretical, but this time we're basing it off of what actually happened. Okay. Theoretical is what we hoped is going to happen. Experimental is what actually happened. Okay. So I've got a blank table here. And I did an experiment with my wife, that's the BE, Becky, and then my oldest daughter, Olivia, then Natalia, and then myself. And then Me and my wife, we actually went out to eat last night, and we went to Ohana's over at Disney. Very, very good. It's delicious. If you've never tried it, go do it. It is a little expensive, but it's so worth it. So there's my little plug. We went to Ohana last night. We braved it. This coronavirus ain't going to hold me down. And I made my waitress do this. So I'm going to add W for waitress. So I made her. And what I did was I gave everybody a coin, and I said, flip the coin 10 times. Obviously, my littlest Natalia, she's only like, 4 right now. So just like, she didn't know how to flip a coin. So she just like threw the coin around the room and started chasing it around like it was a game, like in a cat. So she had a lot of fun with it. My oldest, she did her best at flipping the coin. But these were the outcomes of our trial. Okay, so my wife, she ended up with heads 3 times and tails 7 times. My daughter, Olivia, ended up with heads 4 times and tails 6 times. Natalia ended up with heads 5 times and tails 6 times. That was kind of amazing because I ended up with the same thing that she did, even though she was taking and chucking the coin around our living room, practically almost breaking my TV. I had to get after her about that one. We don't break Daddy's TV. And then last but not least, our waitress, she laughed kind of the whole time and thought I was kind of nuts when I asked her to do this. She flipped tails 3 times and heads 7 times. So there's all of the data. So if we look at this and, we work up an extra column down here, let's call it the total. If I look at this experiment totally, what's cool about it is I just had people be able to run an experiment that I didn't want to do myself, where I had, them flip a total amount of 50 times. Okay, because everybody flipped their coin 10 times. So that's 50 trials right there. So in the end, what we have found is that heads came up 24 times, tails came up 26 times. So if you're looking at this and you're kind of figuring some things out, you're going to notice that the probability of heads was 12 out of 25. That's a reduced fraction because all I did was take the 24, put it over the 50, and reduce it down. That's 12 over 25. Or in other words, it's a 0.48 or 48%. Okay, the probability of tails ended up being 13 out of 25, which is a 0.52. Now, if you look at this and you think about back to our theoretical, I talked about this in the beginning. If I flip a coin, the probability of heads should have been 50%, a half. The probability of tails should have been 50% or a half. Why is there discrepancy? Why didn't my experiment yield what the theoretical was? 50-50. Okay? And in class, we would have a discussion about this, and I would ask you about why is there discrepancy in here? And hopefully many of you'd be like, well, Mr. Armstrong, the weight of your coin sometimes varies. Okay, especially if we were flipping pennies. There is a certain date, I can't remember what the date was, but they changed the material that pennies were made of. Original pennies, they were usually made out of copper. The original penny was. But they found that copper sometimes got to be a little bit more expensive. And so later on, they switched to a copper kind of coating on the outside with a zinc type of material used on the inside. So pennies got a little bit lighter using that zinc copper combination. So there's a change in weight depending on maybe the date of the penny that you could have been using. We were flipping quarters, so that's neither here nor there. But if the etching on your coin. Some of our coins have changed, the style of them. Quarters, some of the quarters had different state backgrounds as we were celebrating, the United States. Every year, I think they produce like 5 different states on the back of quarters. And so there are basically 50 types of quarters that were out there, including the regular American quarter with, the head of the president on the front, the eagle on the back. All of those have different etchings, which again changes the weight of your quarter. Then you could talk about wind resistance and, flipping styles, because obviously my flipping is like a normal, put the coin between my pointer and thumb, flip it up in the air, it spins nice rotations, I catch it and I flip it and slap it on the back of my hand, versus my daughter Natalia, she's taking the coin, whipping it around the room, and then going to see what the result was. Okay. So obviously there's flipping style and then wind resistance and things like that. Lots of things that could affect this, because we're now actually experimenting. Okay. But the cool part is, I'm going to tell you, the experimental and the theoretical are actually going to work out. Okay. Flipping a coin is really a 50-50%. Okay. There's 50% of the time you should get heads, 50% of the times you should get tails. Why there's a big discrepancy right here is because we actually didn't do the experiment enough. Other than, you've got all those other factors you talk about, but I promise you, if you did this experiment more and more and more, and now when I say more, I'm talking about not like 50 more times, I'm making it 100. Okay. Not even doing it 150 times. I'm talking about if you take, and I take this picture straight from our book, and you do the experiment 1,000 times, 10,000 times, 100,000 times, look at how the probability's coming out. Right there, 0.4988. That's getting closer and closer to that 50% that we're talking about. And so with experimental probabilities, even though the experimental probability may not come out to be what the theoretical is, you did that experiment a whole heck of a lot. Like if we probably ran that experiment 1,000,000 times, you're going to see that number get closer and closer and closer to that 0.5. This is what we call the law of large numbers. The more you do it, the more it's going to hone in and zone in on that theoretical probability that we talked about earlier. Kind of cool. And you can see, tossing a coin, how it varied for their experiment. When they tossed it 10 times, it was 0.4. When they did it 50 times, their probability was 0.54, which was 54%, But the more that they do it, the more you see that it hones in on that number of 0.5 or half. Kind of cool. So what I have left here are 2 examples, and we're going to find some probabilities. So they did an experiment, or they ran a survey, okay, of the number of people in the United States living alone. They did a survey. This is where I said you see a lot of probability with experiments comes from surveys, because surveys are kind of experimental in nature. So they have males and females, and they have all of them broken up into their age brackets, and then you get totals for everything that happens down below. So when you do this, it says down below in the directions, find the probability expressed as a decimal rounded to the nearest 100. So here, once you get your fraction, you're going to actually go into your calculator and divide it and round to the nearest 100th for these. If it didn't say that, then you would be having fractions for your answers, and you'd have the calculator run that for you. But because this says round, we're going to round. Okay? So let me show you what the probabilities I want you to find. Remember, the probability, again, in order to do this, take what you want over the total number of trials. Okay? Take what you want to happen over the total number of trials. So when you look at these probabilities, I want the males on top over the total number of people we talk to. And the second probability, I want anybody that's 25 to 34 on top over the total number of people we talk to. And then the last one, the women that are 15 to 24, okay, I want that on top of the total number of people we talk to. Okay? So pause the video, give it a shot. Okay. So, males. How many males did we talk to? Because that's what I want on top. We talked to a total of, so let me zone back in. So we want the probability of males. Cool thing, again, we already know the bottom number to all of these. Hopefully you went up here to the document and you looked right here. Here's the total number of people we talked to, 29.3. Again, this is all in millions. So 29.3 million people. So down below here is 29.3. 29.3. All of these are 29.3 because that's the people we talked to. Okay? So on top, we want the males. So how many males were there? Right there. There's your total number of males because this is the male row. So all the way over here, here's the total. So that's 12.5 on top of here. So all we're going to do is we're going to go to our calculator, move that back where it was, and we're going to put 12.5 divided by 29.3. Don't use the fraction key this time. Don't use that, but you actually want to do the division because we are rounding to the nearest hundredth. Hundredth means 2 decimal places. So we're going to take 12.5 divided by 29.3. Again, you just go to the calculator and type that in. Any calculator can do this. So 12.5 divided by 29.3 equals, rounded to the nearest hundredth, is 0.43 because the 6 after the 2 says, hey, 2, round up. And there you go. That's all they want. 0.43 is the probability, or in other words, 43%. All right. So 25 to 34. So we want on top how many people that we talked to were 25 to 34. All right. Here's 25 to 34. Here's the total. It's right there. So on top, we talked to a total of 3.8 million people to 34. Woo! Crazy moving. 3.8. And again, all you're going to do is go to the calculator. 3.8 divided by 29.3. Hit enter. And you round to the nearest hundredth, which is 0.13. Because the 9 says, hey, 2, go up. And then last but not least, we want to be a woman 15 to 24. So here are the women. Here is the 15 to 24. So how many people is that? 0.8 million people are 15 to 24 that live on their own and are female. So 0.8. All we got to do is go to our calculator, take the 0.8, divide it by 29.3, hit enter, and rounding to the correct hundredth is 0.03 because the 7 says, hey, 2, up. There you go. I got one more experimental problem, and that's 11.4. When we get to section 11.5, we take everything from 11.1, 11.2, 11.3, and 11.4. We put it all together. There's nothing new in 11.5. It's just putting it all together and finding probabilities using some of those counting techniques. So again, here's the last one. Let me give you the full page. Find me those 2 probabilities. Just so you also know, sometimes the picture they might give you, the little table, like this guy that's up here, sometimes they do not put in the total rows and columns, so you might have to figure some of that information out, just to give you a heads up. Sometimes you have to find the totals. But in these examples I've used, I've given you the totals. So go ahead, pause the video, find me these last two probabilities, and that wraps up 11.4. Okay, so right here, I want the probability of having less than 4 years of high school. Less than 4 years. Well, how many people is that? Well, here's the less than 4 years. There's the total, so it is 29. And again, we already know what both of these probabilities are going to be out of, because if we look up here, here is the total number of people we talked to. Okay? So the directions also say these probabilities should be as a fraction. So this is, again, where you need that calculator, because here's where you're going to get some of those large numbers that, let the calculator do its work. So we go into our calculator, we put 29 over 174, and we let it reduce, which it does reduce to 1/6. That's the fraction that they want. Okay, so no rounding on this one. They actually want you to have the fraction. Okay, we also know down here that this guy right here is going to be over 6. Okay, or sorry, not 6, 174, because that's how many people we talked to. We just got to figure out the top number. So we want to know how many people are a man with 4 years of college or more. Okay, well, here's the men. Here's 4 years of college or more. So my top number is 23. So we come down here, we slap a 23, we go to our calculator, and we 23 fraction over the 74, and that does not reduce. So the 23 over 174 is the final answer, and that's what you would put in the My Math Lab. And that's it. That's probability. Again, like I said a couple of seconds ago, 11.5 takes everything from 11.1, 11.2, and 11.3, which are counting techniques, and we combine it together with the 11.4, and we find probabilities using some of those counting techniques. All right. Thanks. See you soon.